Hello class, welcome back and we'll continue doing the pre-quiz review for quiz 3. So we covered diodes and BJTs in my previous recording. Now in this recording I want to finish the remaining 2 chapters that will be in the quiz, and that is the chapter on MOSFETs, the first one, and then chapter 13, which is digital CMOS digital circuits. And of course, like I promised, in CMOS digital circuits we'll only look at part A material and not part B material. Part A was the week 11 material. Okay, alright, so let's get started. You're looking at my slide on MOSFETs. I don't know what slide number, yeah, it's slide number 10. And again, I've tried to pack it with a lot of information, so excuse the fact that it seems so densely packed. But all the information that you do need to know is here. So let's look to see what the information is. So starting from the top left, there are the MOSFET types, the NMOS and the PMOS transistors, and I hope by now most of the basic material is something that all of you have understood about MOSFETs. The fact is that there is an insulation area right there, and it's a silicon dioxide based insulator that first and foremost creates a capacitor, right? By having a metal on the top and conducting material below, you put an insulator in the middle and you create an insulator. Once you apply a voltage to the insulator, you start to create a channel, right? And that is that N-type, induced N-type channel. It's created through depletion, and that's why you have this depletion region also shown here. Then if you apply another voltage in perpendicular direction to this gate to body voltage, that begins the flow of electrons, right? So that is the basic idea behind the MOSFET. And you have the MOSFET in both types. That means the N-type and the P-type, right? The P-type MOSFET is called PMOS, the N-type MOSFET is called NMOS, and there are 2 sets of voltages that need to be applied, one to the gate circuit, so the gate to source. The source is shown grounded generally, and the drain has another voltage applied to it. And so with those 2 voltages, you get the necessary amplification or switching action on the transistors, right? Of course, for PMOS, the voltages are reversed. So for NMOS, the voltage applied at the gate is positive, and the voltage applied, I don't show that, I picked, I guess, the wrong drawing here, but there is a voltage also on the drain, and that drain voltage is also positive. For PMOS, it's the opposite. The gate voltage is negative and the drain voltage is also negative. That you can see here, right? Yeah. Okay. So there are some new parameters or constants that get introduced when we start talking about MOSFET circuits or MOSFET behavior. First of all, there is this VT, right? That's called the threshold voltage, and it's different from the thermal voltage that we saw in BJTs, right? Don't confuse the two. That has a value about 26 millivolts. This is VT, which is V thermal, and it comes in 2 forms, VTN or VTP. VTN is for NMOS and VTP is for PMOS, and the value is about 0.3 to 0.4 generally. So that's one value. Another value that is important to understand is what's this called this V over drive voltage, VOV. And the VOV is actually whatever is the gate to source voltage that you apply here to create the capacitance. That gate to source voltage minus the V thermal gives you V over drive. So one other important factor to remember is that if cutoff in NMOS or MOSFETs, cutoff means that the VGS is less than VT, right? If that condition exists, then you say that there is not enough forward bias or forward voltage on the gate to even begin the process of creating a capacitance and creating a depletion zone and all that. So cutoff means VGS less than VT. We don't see that too much here obviously in this chapter, but the next chapter, cutoff and saturation are important for switching operation. But here we work, cutoff and triode for switching operation. Remember, for MOSFETs, saturation region is the important region because it's like the active region of BJTs. All the amplifier behavior we analyze when the MOSFET is in saturation, and the other two zones are called cutoff and triode. Okay, all right. So important thing is V over drive voltage, VOV, is the difference between the gate to source applied voltage minus a constant VT, which is a threshold. A few other important relationships that I've tried to summarize here. Obviously, we are very interested in current, right? And current is generally shown, ID is the value of current that flows all the way through the circuit. Now we show, for biasing and for understanding the physics of the device, we show the circuit like this, but a more real circuit actually looks like this to the right, right? You have the bias voltage, the gate to source applied at the gate, and the other voltage is picked off of the drain, and the collector, not the collector, obviously the source here with the arrow, that is grounded. So ground is these three terminals for an NMOS and the opposite for a PMOS. Here, like I said, the negative voltage gets applied to the gate and also to the drain, while the source is grounded. Now generally we don't show a positive ground, but that is one way to help understand how to wire these circuits, right? For a PMOS, the ground or the common point is actually the positive, while here is generally negative. So the drain current, which is the current that flows through the entire device, is given by this formula, and these factors, these parameters are also nu. Well, mu n is the electron mobility. I think we saw that in the first chapter on semiconductors. COX is something new. It is related to the capacitance that's created here by applying just the gate to source voltage. So that they always come together. And then there's a W by L, which is the width by length, and you see these factors quite a bit in the formulas in PMOS, NMOS. So I hope by now you become familiar with them. If not, please, it's not too late, become familiar with them. And then the overdrive voltage appears in many forms. Here we are not showing it as overdrive, but obviously this is overdrive. So this is the full expression for the current, the drain current, but a big chunk of it is actually just GDS. This is called the conductance, which is a factor, which is almost a constant because most of this stuff stays fixed. So we define something called GDS, the conductance, and there's an opposite to the conductance called the resistance or linear resistance. And so both these are important to remember. And then you can write the drain current as voltage by right, V by R. That is because GDS is a conductance, it's the opposite of resistance, 1 by resistance. This formula also makes sense and is useful. So there is this factor Kn prime, which is the product of this, and then there's a Kn, which is the product of this, and W by L. So these are new factors that we were introduced to. This is called the process transconductance parameter. This is called the transistor transconductance parameter. So big names, but you will recognize that they keep appearing when you have to solve problems. So please become familiar with all this and this basic circuit and all these various voltages here. So there's the gate to source voltage, the gate to drain, and then there's a voltage here which is the drain to source, VDS. Okay, so that was the top portion. In the middle, I start with introducing the graph that relates the ID, the current, to the drain to source voltage at a fixed VGS. So if you fix the gate to source and you vary the drain to source, this is how the drain current changes. So what we see here is, in the beginning, it's called the triode region, where the VDS is low and it's lower than the overdrive voltage VOV. It has this nice exponential form. Once the drain to source voltage hits the overdrive voltage, from then on it's called the saturation region for a while, and then it falls off into the triode region, into the cutoff region. Okay, but this slope is the GDS that was introduced here, and this is the value for GDS. Actually, GDS has many formulas, but one formula is this Kn prime, W by L, and V over drive voltage, which is what is shown here. And then the current here, the saturation current, or the current when the transistor is saturated, stays pretty fixed, except if you take into account something called channel width modulation, channel length modulation, which I've tried not to bring in here because it just confuses everything. But generally we assume that the drain current is constant, and these two formulas are very important, right? In fact, this one, ID equals half Kn VOV square, is an important relationship, because if you are given, this actually is similar to the relationship we saw for BJTs and diodes, right? There is that collector current that is the product of IS, which is a constant, times e to the power voltage, right? So similar thing here. The voltage is the input, the current is the output. Here we have a square relationship, and this everything else is constant. So this ID equals something times V square gives you the current in this drain circuit, and this voltage is actually the voltage on the input side, right? So this relationship is important, and this only holds when we are in saturation, which means the drain to source voltage has to be greater than the overdrive voltage. That is the basic condition that defines saturation. Okay. We have this other set of graphs which connect the VDS to ID, but for different values of the drain, the gate to source voltage. So for different GSs, right, VGS. So this is one VGS, this is another VGS. You can draw different shapes of these, and that also has its own use. It helps to create this VTC graph, which we'll come to in a minute. So I hope these graphs are clear. Another important thing to realize is cutoff here. It's shown as VGS less than V threshold, right? That's important to remember. Another factor you'll notice is cutoff also means that the V drain to source becomes VDD. Okay, so there's two definitions for cutoff. On the input side or on the gate circuit, we have VGS has to be less than V threshold. On the drain side, when the drain to source voltage becomes equal to VDD, the supply battery, then also we call it cutoff. That means there's no current flowing in the drain circuit. Okay, now let's talk about a voltage amplifier. So this equation tells us that you can affect the current in the output circuit, which is the drain circuit, by varying the input voltage, right, the overdrive voltage, which by the way is here. So, but let's say we want an input voltage to affect an output voltage, right? Then it makes it easier to understand, and then we can call it a voltage amplifier. So to be able to do that, just like we did it for the BJT, you run this drain current through a resistor and you pick the output voltage off of that resistor. Then you can write this nice KVL that says V output equals some fixed value minus the independent variable ID times RD. You can modify that to show it in terms of input voltages. If you don't want to mess with the current, then VDS in output voltage equals constant minus something times input voltage, right? So the input and output voltages are related in this way. So that brings us to the question of voltage gain, right? Voltage gain we define as the output voltage divided by the input voltage, or actually the change in the output by the change in the input. And that can be, there's a number of ways to calculate that. Here we only use the known constants like Kn and overdrive voltage and the Rd. Same thing here. But here the top version of the voltage gain equation formula, we bring in another factor called Gm. Remember, here we had a GDS, we call this conductance. This GM is called transconductance, and it only applies generally to small signals or small signal analysis. Okay, so keep that in mind. Keep the fact that there's a few ways to calculate voltage gain. I won't go into too much detail here. If you're interested, you should be interested. You should look through my notes or read the textbook and become comfortable with all these. Lastly, I wanted to talk here about the VTC, the voltage transfer characteristic, which is just a relationship between input voltage on the x-axis and output voltage on the y-axis. When we say input side, we mean the gate to source, right? This is always the input, or this is the input. The output is what you get out here off of the drain circuit. So this is the drain side, this is the gate side, and the relationship is like this. So initially there's a cutoff region and then it falls negatively because the gain is always negative, and there is a saturation region in the middle, and then there is a triode region at the end. In the triode region also there's something interesting, and that is the fact that the MOSFET behaves actually like a linear resistor. Part of this is considered linear, and you can actually model the behavior where it's just like a resistor. That means the output, the voltage, the current is proportional to the voltage, and that also is used in some applications. But mostly we are interested in this chapter in the saturation region between A and B, where this looks like it's a nice linear, a big part of it is linear, and there is a magnification effect. That means if you look in this circuit below, a small change in the input side, that is on the gate to source, gate to source circuit gives you a big magnification on the output side, which is the drain to source circuit. Okay, so that amplification happens if you operate in this linear region between A and B, and you have a good bias point right in the middle, the Q point, so that you have a nice swing on either side of your input signal. Okay, So that was the middle row. Now we come to the bottom row, right? The bottom row, we have the transistor amplifier circuit and its details, and here you will notice that we bring in the small signal model. So in the small signal model, which by now I hope you're familiar with, we have the drain, the biasing voltage and the signal voltage shown separately in series, and as long as the signal is small signal condition, meaning the VGS, the signal is less than much less than twice of the overdrive voltage, then we say we are in small signal, and then you can then use the linear form of the output equation. So the output equation, I've only shown one here, which is the drain current, but you know how to write for the others too in the same way. The drain current, the total drain current is the drain current, the bias drain current, DC bias, plus the signal drain current, right? And so we start using the small signal parameters. In this case, I've already talked about GM, the transconductance, and that's defined and identified through these formulas. I hope you become familiar with these. Now the gate circuit is always open, there is no gate current, so there is no gate input resistance, it's infinity. But the model, one of the models is drawn like this. So this also can be modeled, MOSFET can be modeled as a voltage controlled current source, right? So this is a current source, but it depends on the voltage VGS and a GM. So if you multiply the two, you get the value of the dependent current source as GM type VGS. If you take into effect the channel length modulation, there's another factor called RO that comes in, that goes in parallel, and then the model becomes like this. And how do you find these RO and the GM, and how is it connected to the voltage gain? Here are some formulas. Okay, so please become familiar with these, because these will be important for problem solving. Okay, we finally come to some problems that I wanted to go through. So here's the first problem. It's a simple one. We are given a MOSFET circuit, an NMOS, and we are asked to find the current ID of M1. What else is given? The fact that this product mu n COX is given, and V threshold is given to be 0.4. Also, if the gate voltage increases by 10 millivolts, what is the change in the drain voltage? So kind of tell us what the amplification is happening here. Okay. Alright, so let me open up my MOSFET's problem and let me look at, I think this is the problem, finding ID, right? Yeah. Yep, 1.8 and Vt is given. Yeah, this WL is 2 by 1.8. So VGS is shown here, and since there's no other resistance or anything, this is applied fully to the gate circuit, gate to source. So VGS is given. So assuming saturation, find ID, right? And the simple formula for ID is this. So you take this product, you take this value, multiply it by WL, and find this overdrive voltage. Now, overdrive voltage is nothing but VGS minus VT. So if you do that, you get an ID of 200 microamps. Sometimes in this circuit, you may not be given ID, but you may be, you may not be given VGS, you may be given ID, right? In which case, you can first solve for the overdrive voltage, the same relationship. You know the left side, you know some of the things on the right side, you can find the overdrive and then find the VGS. So be prepared for both types of questions on find ID or find overdrive voltage. Then we assume saturation, but we have to check for saturation. Are we really in saturation? So what is the main rule to find whether it's saturated? We have to check if the drain to source voltage is greater than the overdrive voltage. If that condition is met, then we say it's in saturation. So how to find VDS, which is the value here, right? So we use that simple KVL formula. Vx, or in this case VDS, is VDD minus IDRD. So if you do that, you get 0.8. So VDS is 0.8, VGS minus VT, which is overdrive, is 0.6. So 0.8 is greater than 0.6, and so we declare that we are in saturation. Now, the part B says if VGS increases by 10 millivolts or 1.01 to 1.01, then ID becomes this and Vx becomes this. So the change in gate voltage is 0.01, or delta Vx of 0.034, right? So a change of 0.01 gave us a change of 0.034, so there's like a 3.4 times gain, right? Okay, so that was that problem. Let me go back to my PowerPoint. We have one more small problem. Here we can just look at this problem right here. I don't have to go to my PDF. Here we are given some information and we are asked to find the small signal parameters GM and RO. Okay, so we are given this mu n COX, we are given W by L, we are told what the drain current is, it's 0.5 milliamps, and there's also a lambda factor here, right? So first to find GM. So first we'll use this formula for GM, right? GM is root 2, actually the whole thing is under one big root sign, but you can split it up like this, but it's root 2 Kn, root 2 W by L, root ID. So if you plug in all these, you get GM as 1.0 milliamps per volt, and R0 is 1 by lambda ID. ID is given, lambda is given, so R0, which is that resistance in the small signal model, turns out to be 20 kilo ohms. So see how to use these formulas given certain values, okay? All right, what is next? I have one more problem, and this is problem example 5.9 from the textbook, okay? Same thing, we are given this circuit which has the small signal source, and it has the biasing battery voltage, and there's of course a VDD and a drain resistor. Okay, consider the amplifier circuit shown here. The transistor is specified to have all these values. There's a Vt is given, Kn dash or Kn prime is given, W by L is given, lambda is 0, so that's nice. Let VDD equals 1.8 and RD is 17.5, even GS is given. So almost a lot of information, almost everything we need is given. So part A says, assuming no signal, that means if this is 0, just find the biasing stuff, the biasing voltages. So find the overdrive voltage. From that you can, well, first we find, I guess, ID, or we can use these formulas here. V overdrive voltage, ID, VDS, and the voltage gain. Then he asks, what is the maximum symmetrical signal voltage allowed at the drain? That means at this input on the drain side, what value can this VGS take up and down, right? If assuming it's an alternating source like this, what peak can it go on the positive and what peak can it go on the negative, so that we are allowed to still be in saturation, okay? That's the question, okay? Alright, so the equations that we'll use, I've tried to kind of summarize them here even before we start to solve the problem. First equation always is the V overdrive is defined as VGS minus VT, right? Then the relationship that connects the drain current to the overdrive voltage is here. KVL on this drain circuit is here, and then finally voltage gain, you can calculate it many ways, but this is one simple way to calculate it, and looks like we'll have all these values anyway, so this may be a quick way to do it, okay? So let's see how the problem has been solved. So this is 5.9. So part A, VGS is given, so V overdrive, VGS is given right here, and also VT is given, right, V threshold. So if you take the difference of the two, you get V overdrive as 0.2. Now, next thing he does is he uses the formula for ID and plugs in everything else, half times Kn bar times W by L times the overdrive voltage square, and he comes up with the drain current. Once you have that, you can easily find the drain source voltage using KVL, which is 0.4. Now you can see that VDS is greater than VGS, right? Hence it's in saturation. So that is the first thing he's going to say. Since VDS is greater than VOV, the transistor is indeed operating in saturation. And how much is it greater? About 0.2 greater, right? Now, next thing he does is he finds the voltage gain, which just uses all these known values to come up with a value of minus 14. Now, we know that we have to find the magnitude of the input signal. How high can the input signal, that means the gate to source voltage, small gs, how high can it go either side before we put the transistor into saturation, or without causing the transistor to go into saturation. So to do that, he looks at what's going on with the output side. The output side, we know that the overdrive is 0.2, ds is 0.4, so there's a gap of 0.2 volts that is allowed on the output side. That is the most you can go without going into saturation in one direction, right? So what does that mean on the input side? You take the output swing allowed divided by the gain and you get the input swing allowed, which is 14.2, right? So on the input side, this is going positive. You can go negative on the output side by 0.2, right? So similarly, on the other side, you have to worry whether you will push the transistor into cutoff, right? On the one side you worry about saturation, on the other side you worry about cutoff, and you will not go into cutoff until the VDS, the drain to source voltage, becomes VDD. Now we know VDD is pretty high, right? VDD is 1.8 and the drain to source voltage is only 0.4. So you have a long gap between 0.4 and 1.8, so you'll never go into saturation. But negative side, you only have 0.2 to work with, which becomes 14.2 on the input side. So just go through this, understand. He also gives you another more precise way of finding the input swing, slightly different, but I leave you to understand that. But you should have a good idea how this problem is being solved, because that is the core of MOSFET amplifier behavior, right? So spend some time and become comfortable with it. I'm going to have to rush a little bit on to my next section because I still have one more chapter to cover. Not the whole chapter, but the summary. And let me expand this. So this is part A of our CMOS digital circuits. So here also I have divided it into three sections. On the top we talk about the basic inverter. Now remember, much of what we are going to do here, as you probably remember by now, is understanding inverters, and more specifically understanding the CMOS device, which is a combination of NMOS and PMOS, why that combination behaves as a nice inverter, right? So that's the whole point of this chapter, or at least the first part of the chapter. Okay, so we start with defining an inverter from your logic courses, from your digital logic course, and I think you know that the output is high when the input is low, and vice versa. So we first also introduced the idea of a semiconductor device, the NMOS, that can function, NMOS transistor that can function as an inverter because it has this nice VTC that has this inverse shape, and hence we can make the device work in this region where it's off and in this region where it's saturation or on or triode, right? And as we swing between the two, we get the behavior of the inverter, right? And it also works out that when the input is high, the output goes low, and when the input is low, that means this region, the output goes high. So that's all natural in an NMOS device, and hence it makes for a great inverter. So this is the VTC. I'm sure you remember that, we just talked about it. Then we have this detailed VTC where we introduce these definitions of these important parameters, right? The output low level, the output high level, VOL, VOH. Then we talk about VIL, that is this value, which is the maximum value of the input interpreted by the inverter as a logic 0. So up until this point, the inverter thinks it's still a logic 0. Similarly, we have another definition, VIN, which is this device, which is the minimum value of input interpreted by the inverter as a logic 1. So from here to here is logic 1, and from here to here is logic 0. And so that range or the limits of the high and the low are important because they help you define how well the inverter will behave and how immune it is to noise, right? So these NML and NMH, noise margin high, noise margin low, noise margin high, are defined like this: VIL minus VOL, VOH minus VIH. The outputs are on this side and the inputs are on this side. So we have an output low level, output high level, and then we have the input stuff. So the noise margins are defined as this. So pay some attention, you must become quite familiar with this because you can expect problems, etc. in the exam on all this. Then we go a little more into detail in the middle row into various types of inverters. So this simple one transistor device is like this, and we model its operation using a switch and a resistor. We talk about a double throw switch without looking too deeply into it, and then we introduce the idea of two complementary switches. So the two complementary switches have a lot of advantages. The top one is called the pull-up switch and the bottom one is called the pull-down switch. So the pull-down switch, it operates when the input is high and it pulls down the input, the high input, to a low value, to ground, so that the output becomes low. Similarly, when the input is low, the pull-up switch operates and it pulls the input up to a high value on the output, right? So that's why the pull-up and the pull-down are defined, and you can see the model circuit here. It also has a resistance and a switch. And then when the equivalent circuit is switching, we said that external capacitances begin to appear, and those cause problems, right? We define power consumption, right? Because there's a resistance and there's a capacitance, we can define some power consumption. And not only that, we then define delays, because once you have a capacitance, it only charges at its own pace using time constants and all that. Similarly, it only discharges also. You never get zero output immediately when there's a capacitance, right? It slowly discharges. So all that causes delays in the rise time and the fall time. So this is the fall time and this is the rise time, right? So those are called propagation delays. And if you define the low to high delay and the high to low delay as falling from a maximum to 50% or rising from 0 to 50%, then the total propagation delay or inverter propagation delay, the TP, is defined as the average of the two. Because you need these gaps, because of the delays, the switching frequency also is a certain value, and that value is F max equals 1 by 2 TP. If you try to put a signal that is switching faster, that means the high to low, low to high is happening faster than this frequency, the inverter will not work anymore. It will have all kinds of strange behavior, right? So the maximum speed of the switching frequency or maximum switching frequency is this. Then we define some factors called the power delay product and the energy delay product. So that is the product of the power consumed, PD, which is the voltage time current, multiplied by the TP, right? And it has another formula like this, and it also gives you, at the maximum switching speed, there's a certain PDP that is this. And then we also define an EDP, which is just this value PDP times the uh, time propagation delay, right? Okay, so that was everything in the middle. Spend some time, become familiar with all these ideas, in particular power consumption, propagation delays, etc. Okay. Next we come to actually putting the two transistors in one circuit, right? The NMOS at the bottom, which is shown here as M1, and the PMOS on the top. Sometimes this is shown as QN and QP in our book, but either way, the two transistors together, generally fabricated on one silicon crystal, it's called a CMOS device, right? It's two devices in one. So when you have this connection, we get the perfect possible inverter, right? Because the benefits of having, we saw the benefits of having the two here. There's no static power dissipation, it's zero, because no current actually flows in a static condition. There is current flowing in a dynamic, meaning when the switching actually is happening, there's current flowing, but once the switching ends and the inverter stays at a certain level, either high or low, there's no power being consumed. So no static power consumption is one benefit. Another benefit is that you don't need a big drain resistor, as we see here, if you only have one device, right? In this circuit you don't see any resistors. So if you're looking to fabricate all this on ICs, integrated circuits, not needing to put big resistors is a big advantage. So bottom line is, the CMOS circuit is the perfect solution for inverters. Then we talk about the matched and the unmatched, because unfortunately the holes and the electrons don't behave exactly the same way in a silicon crystal, right? We know that. So because to get them to be matched, you need to have the area of the P portion of the silicon to be much higher than the area of the N portion, right? Because the hole mobility is much less than the electron mobility. So to have a matched pair of transistors, if the QN and the QP have to be matched, then because the lengths are generally assumed constant, the same in an IC, so the width is the only thing you can vary. And so what we see here, is that actually part of this went away, but it's actually, yeah, that should be the full formula. The width of the P side will be 2 to 4 times the width of the N side. Okay, all right. Then there is the unmatched case, right? And we'll do some problems so you'll understand it. And look at the unmatched here. I'll see if I can take this out. Yeah. So whether it's matched or unmatched, you have for the CMOS inverter, we redefine all these, right? These noise margins, the output level, the input level, we create formulas for all of those. And so this VTC is for an NMOS device, and here we see that the two transistors behave in opposite ways. They kind of cooperate with each other, right? So we see that in this drawing, and I showed you other drawings also in the notes. When one of them is on, the other is off, and vice versa. So using all that logic and all the physics and all the mathematics, we have these set of formulas. So we get Vm, this center voltage, which is the dividing point between when a transistor goes from on to off or off to on. That Vm is exactly VDD by 2. That's an important relationship. Then we have these formulas, please look them up in your notes, for V, these IL, the NOS margins, they're all shown nicely, and they're all dependent only on the VDD and the V threshold and the mu and the W and so on, right? So if you know all that, then you can find these noise margin values. On the right is one more set of equations, the very last. These all relate to finding the propagation delays, right? So to find the high to low propagation delay, there's a formula. To find the low to high propagation delay, there's another formula. And as it turns out, there's two different methods to find them. One method is called using average currents. Another method is called using equivalent resistances, right? And we did some problems already. We'll do a couple more before I'm done here to use these formulas to find the propagation delays for CMOS circuits, CMOS inverter circuits. Also, there is this one important idea about how to find this capacitance. We introduce the capacitance here as causing these delays and causing power consumption and all that. And so that capacitance is not a simple number, it's the sum of a lot of other individual capacitances, including internal and external capacitance, wiring capacitance, capacitance gate to body, gate to source. So we did some problems on how to find this capacitance, right? So this was all the theory that we covered, and I hope you will go through your notes and become familiar once again and revise your knowledge before you take the quiz. Okay? Alright, so I have only two problems, and once we finish with that problems, I'll be done with this recording. So let's look at the first problem. This is from the back of the chapter 1327. What does it say? It says, a CMOS inverter is fabricated in a 0.25 microamp process. I've told this I think a few times. This 0.25 micrometer means that the length L is 0.25, right? So sometimes they may forget to give you the length in the problem, but you should know that when they give you this information, that is the L, okay? Along with that, we are given the VDD, the bias voltage. We are given V threshold N and V threshold P, both equal to 0.5 in magnitude. Of course, VTP will always be negative, but in magnitude they are equal, and that kind of simplifies calculations later on. Then we are given this Kn prime value, which is mu n times COX 3.5, and we are also given mu p times COX, which is a different value, right? That's because mu n's are different and also COX's can be different. So these are two different values. In addition, Qn and Qp have L and W by L of n is given, not by W by L of P, but W by L of n is given. So all this information is given, and then we are asked to investigate the variation of Vm, which is that middle point, with the ratio Wp by Wn. So as Wp by Wn changes, we got three cases here. What happens to Wm is the question that we have to answer. One of them is the matched case, and that's given Wp equals 3.5 times Wn, right? The width of the P is always much larger than the width of the N area, right? Or N section. So that's given to be 3.5, and that's called the matched case. When they are set equal, Wp equals Wn, then it's the minimum size because the area is the minimum possible, but then the performance, the noise margins won't be so good, and the propagation delays will be higher. Then between this and this, there is a compromise, there's a middle point, and that is generally apparently what's used a lot in the industry, and so that is where Wp becomes twice of Wn. So for all these, estimate what happens to Vm and estimate what happens to NML, the noise margin, okay, and also the silicon area. So all this is what we have to look at. So let me open up my PDF. So this is the PDF called class problem, chapter 13, class problems, part A .pdf. So let's look at this problem. Yep, I think this is the one, 1327. Yeah. Okay, so it's on page 7. Okay. So to repeat everything that's been given, VDD is 2.5. That means VOH is 2.5, VOL is 0, VT is Tn, and this is the threshold voltage, so that's given, right? And these values are given, mu n COX, mu p COX, and L is given. W by L, N is given. Okay, so find Vm, find these noise margins. Now the reason I write here VO output high, because it's a CMOS, you can go straight away to these values, right? The output high is always VDD and the output low is 0 volt. So that's another big advantage of having a CMOS, because the source, the biasing voltage becomes the high and 0 becomes the low. Okay, so with all that information, and the area has this formula W times L plus W times L on the P. So first let's start with the matched case. Because mu n is given to be 3.5 mu p, that means Wp equals 3.5 Wn. Actually this is given, we conclude that this is also true because they are the same thing. So Vm should be half of VDD, this is the perfect case, and that's 1.25 volts. Now VIL, we have the formula for this, you can look it up in the table, and that comes out to be 1.0625, and hence noise margin high, noise margin low is the same value, okay, because it's a CMOS. What's the silicon area? Wn Ln plus Wp Lp. Ln is the same for both, and Wn and Wp we know they're related by 3.5. So if you add all that up, you get 0.42 micrometer square for the silicon area. Now to look at the minimum size design, where you set the two to be equal, then you come up with this value for R as 0.53 like this, and then the Vm is not VDD by 2 anymore, but it becomes, using this formula, it becomes 1.02. So Vm is reduced from 1.25 to 1.02, which is an 18% drop. Silicon area becomes 0.19, so you are obviously reducing the silicon area, so you get a savings in cost there. You get a 55% drop in area, but the problem is your noise margins have become worse. Okay. Similarly, WP, the compromise design, again you calculate R like this, then you use it in the formula and you come up with 1.15. So the Vm drops by 1.25 to 1.15, which is a 0.1 volt drop, or it's an 8% drop. So silicon area is lower, right? So what has happened, so the drop of area went from 0.42 square to 0.28 square, or 33% reduction. So I've tried to summarize everything here. Area drops, but the NML, the noise margin, also drops. So in a way the performance is not so good, right? The performance is really, for the matched case we take it as the best, but not the area, which is the worst. But the minimum size, you get a big savings, but the noise margin drops by 18%. The compromise solution, the area is not as great in savings, but the drop is not so bad. The drop in noise margin is not so bad. Okay. All right. So that was one problem we looked at, and what else do I have? Okay, we have one more example, and this is from the textbook. It's example 13.5 on page 1103 in the textbook. Here we are given a lot of values again for the transistor, for the CMOS. We are even given a C, and we have to find the propagation delay in this case, right? Find TP LH, TP HL and TP, which is the average of the two, and use both methods, right? The average current methods and the equivalent resistances method, and compare the results. Also, one last piece that says if VDD is originally 2.5, if it drops to 2, how much does the propagation delay change? So that's the question. I know I'm running slightly late, but let me finish this so you guys know how the problem is solved, and it will benefit you in your quiz, guaranteed. So page 1103, I can close this. Let me go quickly to 1103. So give me a second while I scroll to 1103. Okay, here it is. So this is the solution, okay, the example. So there's a lot of values given. You have to, if you're using the average current approach first, the important thing is to find alpha n first, right? And there is a formula for it. It's equation 1365 if you want to look it up. But you have to find alpha n, then plug it into another formula, which is 1364. And with the combination of these two, we come up with, or he comes up with, T high to low as 41.2 picoseconds. He also says since the Tp equals the Tn, absolute values are the same, alpha p equals alpha n, so you don't have to calculate alpha p again using this formula. You can directly go to calculate the low to high, and that comes out to be 72.1. And then the Tp is the average of the two, and that's 56.7. Using the other approaches, which is a bit simpler, you only need to find two resistances, Rn, but it's still a two-step process each. Rn is this, it is 8.33, and there's an equation there, you can look it up. Then you find TPHL using the time constant method. So the C value is given, the R value we just found, you multiply that by 0.69 and you get 57.5, which is slightly higher than what you get in the previous method. Similarly, you find the TPLH, right, which is 69, and here it was 72. Then if you take the average, here it comes out to be 63, while previously it was 56 by the other method. Okay, so these are the two methods. Please learn how to do this, get some practice so that you don't make mistakes doing these calculations in the exam. Okay, there's also a part B where he's asked what happens if the voltage, the VDD, drops from being 2 volts or 2.5 to 2, right? So I think the top value here, no, this value is VDD, that changes to 2 in the denominator here. So the average average or the final TP, the propagation delay calculated, becomes 87.5. So as you can see, by reducing the source voltage, the VDD, from 2.5 to 2, the TP has gone up to 87.5. It has resulted in increased propagation delay. Of course, you should use the comparison. To compare, you should use the same method, right? We did this using the average currents method. You must compare to the previous average currents method to know how much the value, the propagation delay, has increased. Okay, so it went to 87.5. Previously, it was 56.7. So there's a significant jump in propagation delay because of that half volt drop. Okay, so with this, I am done with the problems and the entire material, the pre-quiz review material. I hope this was beneficial. Whether you follow this or not, please spend some time going through all of the material and the solved problems and the homework problems and the examples for these 4 chapters so that you're well prepared for the quiz number 3. Okay? Write to me if you have any last minute questions. I'm happy to help you. But don't just sit on your, if you don't understand, ask for help, and get better prepared. Okay, thank you and good luck.